Great to be back at BSidesDayton. It's great to see BSidesDayton back after a little bit of a hiatus. Hopefully it comes back next year, but if not, then year after that. But yeah, it's always just great to have a great local conference. My topic today is called Definitely Not Secure, DNS. And I got some live hands-on keyboard hacking demos and so forth because nothing ever goes wrong with those. Thank you. And so for those, if you haven't seen me speak before, I've spoken, as you might have guessed, a lot of places based on what I talked about earlier. My name is Matt Scheurer. With that, let's go ahead and give this talk started. I work for a big, well-known organization. The corporate communications folks don't like me talking about it. If I mention where I work, that comes with more strings attached, and you can find in a 1,000 thread count blanket. So we're just going to leave that out of the way. But I'm Vice President of Computer Security and Incident Response. I have years of all kinds of InfoSec experience. If I have a bread and butter, it's mostly digital forensics and incident response. I am on social media, so do send me a connection request. If you're on LinkedIn, love to connect with folks. And if you're on the other platform, try to do follow backs and all that sort of thing. I do some volunteer work. I'm an official hacking is not a crime advocate. That's not to say that cybercrime is not a crime, because it is. There's a big difference between cybercrime and actual hacking, like you can do it at BSidesDayton with villages, workshops, capture of flags, all sorts of other things. When you have permissible use, when it's your own stuff and it's fair use, that's real hacking. I'm on the advisory board for the Warren County Career Center IT and cybersecurity program because I have issues with how we try to teach information security. We want to teach people a lot of times how to run, but they've never learned how to walk or crawl before that. And this is my attempt to try to make sure that we can try to fix that issue. And I think this talk is very much in line with that mission. And then also, I'm a technical advisor for WAMSA, which is the Women's Security Alliance. They're always looking for mentors and mentees. If that speaks to you, do check them out. Quick disclaimer is, yes, I do have a day job, that the opinions expressed are based solely on my own experience. They do not express or reflect the views or opinions of my employer. So today's agenda, I'm going to talk about DNS essentials. Some of you may know these, some of you may think you know these, and then you'll find out, well, maybe I didn't know as much as I thought I did. And some of you might be super experts and know it better than me, which is fine. But I'm going to make sure we all start from the same place. And then I'm going to go into DNS tools and do some demos there. DNS attacks, do some demos there. The slide deck is available in my GitHub repo. Go ahead and grab a copy of that if you want to download it, share it, do whatever. So the definition of DNS is actually domain name system. And you will note that the S does not stand for security. The domain name system, as I like to describe it, I like KISS definitions, not the band KISS, although I listen to enough of their music, but they keep it simple, stupid, so I can keep it all straight in my mind. Not calling anybody here stupid, that's me. Anyway. I call it this, the vanity protocol making internet network addressing human-friendly. That's the simple definition I like to roll with because I think it makes sense and it doesn't get too deep into the weeds where people can understand it. DNS gossips a lot, and that's one of the issues that we'll demo and we'll talk about. So what do I mean by that? I've got some leaky DNS zone demo I'll be doing later on, but also DNS. If you sat in on the first talk, right after the opening announcements, you heard about stuff being in plain text and DNS requests and so forth. That's the norm. It's possible to encrypt it, but that's usually not the norm. And so it will tell everything about you, where you're going rather, in your traffic, and you can't really refute it or deny it. I've got a demo for that. And then also, sometimes organizations aren't particularly good at pruning their DNS zones. So what happens is they leave stuff in their zone records they maybe didn't intend to, and it just never gets removed. And that is a field day a lot for adversaries. DNS on the OSI model, because I like to talk the OSI model. We're going to talk about IP address. So IP on the network layer, layer 3, is really the first point we have. And then transport layer. I've bolded UDP because most DNS traffic happens through UDP. There's some exceptions that I'll talk about here in a moment. There are, so TCP, we'll talk about where and why it uses that. Port 53 is the default DNS port, and we'll cover the exceptions there as well. So most of it's going through UDP, port 53, and then finally at layer 7, the application layer is where DNS actually works. So I talked about mostly 53. We'll talk about, or for UDP, we'll talk about TCP port 53 and those exceptions where it'll use TCP. Early implementations of UDP had a 512 byte limit, which is pretty small. More modern implementations use a 4096 byte limit. So anything that's exceeding that for DNS is going to roll over to TCP. DNSSEC, which I'll talk about a little bit later, will also use TCP because it's too much information to squeeze into that small of a byte limit. Zone transfers, that is heavily restricted today. Once upon a time, people would put a lot of their internal addressing and they would put it in their public DNS zones, which would come back to bite a lot of places, a lot of people. That's why it's much less of a common practice. And also, you used to be able to connect to somebody's DNS resolvers and dump out all the zone contents. And if it had private information in there, well, they had that too. Now they can start to footprint the infrastructure without even touching your network, other than the DNS resolvers, which you may or may not be maintaining yourself. Other TCP ports. So there is DNS over TLS. It uses port 853. And then there's also DNS over HTTPS, which uses, like most HTTPS traffic over port 443. And those are, by and large, the bulk of the exceptions you run into. Everything else tends to be over UDP 53. It's important to note as well, that's enabled in most environments. It's very rare that somebody would try to block that at the firewall because then nobody could resolve external addresses and that would make it a challenge. So it's very easy to sniff or piggyback into DNS traffic. I'm going to talk about the foundational DNS records. This is not an all-inclusive list. There's others, but these are the ones you're most commonly going to encounter. The A record is where you have an IP address and you point it to a domain. Very simple. Let's pretend it's not Samsung's. Let's pretend I had the IP address 123.45.67.89. If I have dfirmat.com as my domain, I would point that IP address to my domain so the traffic on the internet knows where to go. And that's the double-edged sword with DNS is in order for something to be resolvable and usable by the rest of the internet at large, there has to be some public record of that. And that's by and large what DNS will do. The quad A record is the IPv6 IP address and the host name. CNAME is short for canonical name. I like to think of that as kind of a substitution record. What do I mean by that? So let's say I started blog.dfirmat.com, but blog.dfirmat.com is hosted on blog.somehostingcompany.server.com. I want people to go to the short name, blog.dfirmat.com, much easier to remember. So that's the CNAME record. I point that big ugly address in for the shortened blog.dfirmat.com so that the internet can resolve it. And also when you look in the browser address bar, it doesn't change. It'll show you blog.dfirmat.com even though the content is actually rendering from this other third party. TXT records are very interesting. They have anything you want, you can put into a TXT record. A lot of times, service providers will use it for verification. So for example, like Google, Microsoft, those kinds of services, if you're using them for your mail and so on and so forth, you have to put in like a verification code to prove you own that domain before they'll just let you have the service. Sometimes that information doesn't need to remain in there, but almost nobody ever prunes that information out. And if you recognize the formatting or look it up, you can figure out what services somebody is using in an environment. That's a way to footprint somebody's environment very passively. You also see SPF records, which are used for mail. And in particular, it's used a lot to say this host, this IP address, this other SPF record, this other stuff is allowed to email stuff as our domain. Well, why would you ever do that? Well, think about if you're using a marketing company to send out surveys and you want the email address to send as survey@difrmat.com, but I'm using some other third-party service. I would basically set my TXT record v equals SPF1 and include those hosts, whatever I need, so that that other domain is allowed to send email as my domain, and it will tell the rest of the internet, don't treat stuff from here as spam because it's allowed, it's permitted. MX records are the mail exchange records. So if I have email on my domain, in order for the internet to know where to deliver the actual email message, I need an MX record. Otherwise, the email somebody would send to matt@dfirmat.com, for example, would have no idea where to actually send the email, and it would just bounce back. NS and SOA. So one is name server, the other is what's called start of authority. When you register a domain, you specify your DNS resolvers that are authoritative for your domain. Now, one of those is the primary by which the other name servers will get the DNS zone information from, and that's your start of authority. And so you can do authoritative lookups, but most of the time, your lookups are some sort of cached version on your local resolvers. It depends on how popular a site is. PTR records are pointer records. That's sort of the opposite of the A record. So if I want to let the internet know that 123.45.67.89 belongs to dfirmat.com, that's the pointer record. And then you have the SRV, the service record. Let's say I have a voice over IP platform that I'm using with my business. That would essentially tell the internet that voip.dfirmat.com actually uses this server, this port, this protocol, so that that communication knows how to establish. And again, there's more of these when I'll talk about DNS. So you have DS is another record type that is used for DNSSEC. But again, these are the most common ones that you'll encounter. TXT records. If you look at RFC 1035, which is very old, and you do the correlations, it doesn't come right out and say 255 character limit. But if you read it carefully, extrapolate what the information in the RFC means, you'll come to understand you have 255 characters that a TXT record can hold as its max. TTL, or time to live values, are the number of seconds before other resolvers on the internet should refresh the cache. Some places will get this wrong. So you might think, well, if I set it really high, just tell the internet to refresh every 24 hours. Well, what happens if I make a change? What happens if I fail over from one cloud region to another? What happens if I switch hosting companies? If my TTL is 24 hours, potentially people won't be able to access my stuff on the internet for an entire day until the resolver cache flushes out and refreshes. Now you can force it, but that's a big ask to ask everybody on the internet to refresh your resolver cache manually. A lot of people may not even know how to do it. I've walked people through it. It's not hard, but you need the appropriate permissions, and getting somebody that knows how to do it is the challenge. So you might think, well, why not set it really low? Why not tell the internet refresh every minute? What happens there is that you will pound your DNS resolvers with an unimaginable amount of traffic for a very busy website, for example. And so you can almost deny a service yourself because your DNS resolvers can't keep up with the number of requests because the TTL is set too low. What I usually recommend is set it at a reasonable time. If you know you have a maintenance window coming up, drop it down. Make your changes, give it a day or two to bake, and make sure that everybody's resolving to the new stuff, and then change the TTL back up to maybe like an hour or something like that. I can't give you an exact number, but the idea hopefully is that you can adjust, allow the changes to happen, and then go back and change it to a reasonable time. DNS tools. NS lookup is pretty universal. That's on Unix-like operating systems, Linux like my laptop, it's on the MacBooks, it's on Windows OS machines, it's on mainframes, it's on a bunch of systems. It's by and large available on just about anything. Dig will also look up DNS records, but the format looks a little bit different. By and large, you mostly see that on Unix-like operating systems, Linux, and it is typically available as an optional install for other OSs and other platforms, but just be aware that Dig may not be available. And my first demo is just going to be real quick to show the differences and what those look like. So let me do NS lookup, type let me do A, and let me do BSidesDayton.com. And here we see two different IP addresses, the 104.21.68.14, we see 172.67.184.160. That's the A records that tell the internet, here's how you get to BSidesDayton. That's the infrastructure hosting the website. Dig is going to work pretty similar. Clear that. Well, actually, let me not clear that. So let me do dig txt. All right, did I mistype that? Hold on. All right, I must have messed something up. Oh, yeah, the A record. Thank you. Good eyes, folks. Get done talking about TXT files, I can't refocus. All right, here we go. You notice this is the same IP address as we saw in NS lookup, but the format just looks different, right? So both commands work for looking up IP address information. I personally tend to like the formatting of dig. I think it looks a little cleaner. But, there's no right or wrong to this. Whatever you have available, use it. Early DNS security woes. DNS security is nothing new. RFC 1535 is dated from October of '93. And it talks about security problem with proposed correction on widely deployed DNS software. Now, the actual vulnerability is older than that. It took them a good number of months before somebody wrote it up into an RFC. But 1993 was quite a while ago, so that should hopefully frame just how long DNS security issues have been a challenge. DNS weaknesses. I talked about UDP earlier. Most of the DNS, unless it's encrypted, is plain text. And I talked about leaky records, and how DNS will gossip on you. That's exactly what I mean. Most of it's plain text. And then leaky DNS zone records, again, the stuff that people don't remove from their DNS zones. So I'll do a captured demo. The other thing is that things are not, well, yeah, it'll tell on you basically. So let me do TCP dump. I'm going to do a capture filter to keep my packet size kind of small. Dash, very, very, very verbose. And just do dash I for any interface. And then port 53. And then write it out to capture.pcap. And I'm just going to let that run. And so if I come over here and I just do a ping-c2, and we'll do apple.com. It's going to try to run some DNS queries. I'll do the same thing for google.com. We'll do the same thing for microsoft.com. It's going to take a while, so I'm just going to kill that. Let me go ahead and do myspace.com. And so if I come in here and I stop the packet capture, and then there's my capture.pcap, so let me clear that, and Wireshark. And let me zoom in here on this. Oops. That's fine. Hold on. Here we go. All right, and so we can see it's capturing my DNS requests. And so try as I might, if somebody's like, hey, your computer tried to talk to myspace.com, and I might try to lie about it and say, oh, no way, dude, it's 2026, brah. Who's trying to go to myspace.com, right? Well, there it is in the DNS records. It's undeniable that I tried to access or reach out to myspace.com. And if we drill into the layer 7 information and I look at the, again, I get a lot of good information here with the flags and so forth, additional records. We can really kind of see here in the PCAP. Here's the query. We can see the name servers that's going through. And again, pretty irrefutable that I was trying to access that particular domain because it's right here in the results and we see what those records are. The other thing I talked about was, hey, some places don't prune their information. Now, long time ago, so long ago, I don't even list it on my resume or my LinkedIn anymore. I worked at a place some of you may be familiar with called LexisNexis. Now, if I was an enterprising attacker and I wanted to understand from a security perspective, what does their footprint look like? What might I want to attack? I can use a site like DNSdumpster.com. Now, there's some command line tools as well, such as DNS Recon that you can get in most any offensive security distribution. But I'm just going to go ahead and let this run through. And it's not really liking it here. Let me try it one more time. Let me refresh the site here. This isn't even touching their systems, by the way. This is completely passive. And so what we see here is we see all of the host records that they have in their DNS zone that's queried back. So I've got those classic A records we talked about. Again, I can look for specific things that might be interesting. Here we get into, like a CNAME. I can see the IP addresses where stuff is hosted. I can really look for things that are, potentially interesting to me as an adversary or an offensive security professional. What's automation API? I don't know, but by gosh, if I want to look for potential API vulnerabilities, there's a nice juicy target for me right there. And so if I scroll all the way down here and look at the TXT records, again, we see all these different verification codes that have never been cleaned up. Some of them may or may not even be necessary anymore. But yeah, oh, look, well, they've got Cisco stuff in their domain. Oh, they're using Canva. If I have a malicious Canva page, maybe that's something I can social engineer and target LexisNexis staff to try to get people to access my stuff. Again, I can see the SPF, so I can see they're using Agari for their email services. Well, if somebody publishes an Agari bypass for email security, that might be something I could try against them. Pardot. We know they're using Zoom. Maybe I can send people a Zoom meeting and make it look real official. There's just a wealth of information if I wanted to try to go after them as a target. And even better, I can just download this as an Excel file and then look at it offline. And anything that is hanging up out there that they didn't clean up, for example, there might be, I might see like a VDI address. I might see a VPN address. Maybe I can even figure out what type of technology they're using. If a published vulnerability becomes available, I have it. So yeah, that's just kind of a quick way to learn an awful lot about an organization without even reconning their stuff by reaching out and touching their own infrastructure. So we talked about leaky DNS zones, DNS hijacking. Really, whoever controls the flow of network packets wins. I don't care if you're talking offensive security professionals or real-life cyber criminal threat actors. That happens through a process. So if a person or a system on a network requests a resource on the local network or the greater internet, it goes through this process. And the first thing, we'll talk a little more about this later, but it'll check the host file to see if there's a definition in the host file to know where to route stuff. From there, it will go to the DNS resolvers that are defined for that particular network. And that will go further on down to other DNS resolvers at the ISP, for example. But again, it'll check the preferred for a little bit. If that fails or times out, it'll go to the alternates. DNS search path is really using short names on a network. So, for example, if I have Matt-laptop is my host name, rather than needing to request the whole fully qualified domain name of matt-laptop.thisnetwork.int, for example, that DNS search path will say, just to automatically append in the background this fully qualified domain part. So all you have to do is try to ping or RDP connect or whatever service is available on the short name. Now, if somebody could put in malicious fully qualified domain name, they might be able to circumvent those short names and send them elsewhere. And then finally, I'll talk about this in a little bit later detail, NetBIOS name resolution. Believe it or not, there's still some places that use NetBIOS in lieu of standard DNS. A lot of manufacturing, for example, some of that technology, some of those systems might be decades old. And so they don't use standard DNS. They will actually still, to this day, use NetBIOS and WINS. So you might think, well, how do I stop somebody from DNS poisoning? DNSSEC, that's really the solution that the industry came up with. And what it does is it provides a cryptographic chain of trust to prevent DNS spoofing and cache poisoning attacks. Sounds good, right? That's going to stop all this stuff, but there might be some shortcomings with DNSSEC. I've heard it said before, and whatever level you agree with this, either wholeheartedly or even just a little tiny bit, but I've heard said many times before that complexity is the enemy of security. Whatever level you agree with that, if that's even just a little bit true, guess what DNSSEC is not? It's not easy. So we have a lack of adoption because it's hard to do it. And even the places that do it, these configuration woes, it's hard to do it and get it right. It's not just super easy, cut and dry, just like adding a DNS zone record. It's actually very hard to do it and have it work correctly and know that it's definitively working correctly. I talked about the host file. Yeah, you can just bypass DNSSEC completely by injecting into the host file, and a lot of malware will do just that. And I'll demo that here in a second. Adversary or attacker in the middle, man in the middle, whatever you want to call it, whatever your preferred acronym and definition there, that last hop going back on the request doesn't rely on DNSSEC. So if somebody can inject into that last hop on those resolvers coming back, could actually manipulate or modify the records. And then finally, typo squatting. So if I look at a domain like BSidesDayton.com, maybe they've set up DNSSEC correctly and it's all working properly. But what if I register BSide without the S, Dayton.com? So BSidesDayton.com, and I make it look just like BSidesDayton.com. And I socially engineer people, and they're not paying attention to where the address is actually going. I don't need to put DNSSEC on that spoof domain. I can roll without it. I could even set up DNSSEC for my spoof domain and get it configured working correctly, and it's going to look like it's legit and secure, but it's not using the actual authoritative, the proper BSidesDayton.com. So that's, again, doesn't matter at that point if you've properly secured and configured DNSSEC and got it working properly. If somebody's just using a typo squat version of the domain and the people that are accessing it don't notice, doesn't even matter. Where the host file lives, on Unix-like operating systems, Linux, it's under /etc/hosts. And on Windows, it's under C, Windows System 32, drivers, etc hosts. Really the same principle. The file does basically the same thing, just lives on two different locations depending on the particular operating system. So let's talk about injecting the host file and actually show what that looks like. So again, if I just do a ping c2 BSidesDayton.com. Oh, it's giving me an IPv6. That would figure. All right, let's go ahead and just do a dig. T BSidesDayton.com. I don't remember. Oh, I'm doing T again. Dang it, Matt. Can't get dig dash TA. All right, here we go. So we see the IP addresses for BSidesDayton. Let's just do a ping -c2 www.google.com. It figures everything's translating IPv6 on me today. All right, let's go ahead and run our dig, and we'll just do the A record here. And so I'm just going to grab this first IPv4 address. Paste that. Oops, shoot. I bet I'm going to recopy that. All right, well, that's ugly, but I can fix it. All right, now I'm just going to append this to the C hosts file. Now, if I do a ping C2, we see that it's actually resolving to the Google IP address. So anything that requests BSidesDayton from this particular laptop, oops, is going to send it somewhere else. And if that's a web server that I'm controlling, I can direct somebody's traffic to a site with malicious content, malicious payloads, click fix malware, whatever I would want as an enterprising threat actor. And a lot of malware will do just that. It's a juicy target, if you will. Another potential vulnerability or potential for an exploit here is a rogue DHCP server. If somebody gets onto a network and sets up their own DHCP server, and either it's shorter path or just out of dumb luck, the network routes it to my malicious, my rogue DHCP server. When you connect a system to a network, if it's using DHCP, it's going to say, hey, I see I'm on a network. I would like to connect to this network. DHCP server, what do you have for me? And the DHCP server in this DORA process is going to send back an offer saying, oh, hey there, how about this IP address, this subnet mask, and these DNS servers, that sort of thing. Client's going to say, yeah, that looks good. I'll take those settings. Rogue DHCP server will say, okay, here you go. Welcome to the network. And again, if somebody's going to rogue DHCP, they're not hitting the real one. Well, what's in DHCP settings? We have a number of things. We have the IP address, the subnet mask, also the default gateway, which is what tells the system, route all your network traffic, your internet traffic, through this IP address. We could actually change that, send it somewhere malicious if we wanted to, something we control. It also tells it, here's the DNS resolvers you use. Well, what if I stood up my own malicious DNS resolvers and chocked it full of bad information? Hypothetically, I could send traffic to wrong places and it looks just like it should from the client side. And then WINS and NetBIOS I touched on earlier. That's the Network Basic Input-Output System. So that is basically the network settings for an endpoint. And the WINS server is really just a database that catalogs what systems or what addresses on the network. It's sort of a little bit more primitive. Well, I shouldn't say primitive because they've been around forever, but basically it's the Microsoft version of DNS before they just don't use our technology, just use DNS. But again, that environment or that shop floor environment I talked about earlier, that's still using NetBIOS and WINS sometimes for network addressing. DNS tunneling, there's a couple different things, command and control, as well as DNS exfiltration. And so DNS can be used for those two things. So if malware gets on a system, command and control, most malware isn't just one and done. It installs and it's ready to go. Most of it these days is multi-stage. It infects the system. It tells it where to call for additional instructions in the botnet. System gets those updated instructions, gets the next set, so on and so forth. And it's a multi-stage process. And then exfiltration is shipping data right out of the network using DNS. Now, it's not optimal or ideal for it because, again, we talked about that 255 character limit and definitely want to bear that in mind, but it is still possible. And so DNS, because it's not blocked on most firewalls, it's allowed, lend itself to that possibility. And indeed, malware has definitely done that. So I'm going to do C2 demo here. There we go, away keyboard. Well, all right. All right, that on-screen keyboard just magically popped up is messing with me. Let me close out the terminal windows and fire up a new one. Bear with me here. All right, now let me do a dig -t txt and I'll do abc.dfirmat.com. So when we make this request, we get back a string in the answer section. Now, it's not human understandable to look at it, but there's some traits here, and that's this string right here I'm going to highlight. Starts with a Z, and what we notice are a few things. One is it's using about the entire alphabet. Doesn't look like there's numbers, but oftentimes you will see numbers in here. You're not always going to see an equal sign or two equal sign at the end, but the way base encoding works is things have to match a certain bit level in order to be decodable on the remote end. And so when you have remainders with the base encoding, it does what's called a pad, which are the one or two equal sign. Sometimes you have those, sometimes you don't. But when you do have them, it's a pretty dead giveaway. And so if I copy that string, and so I'm just going to echo it. Go ahead and open up a new tab here. It's not privileged. So let me go ahead and echo that string that I copied. And I'm going to pipe it into base 64. -D to decode. Ampersand, ampersand, echo, hard return. And we get the result. Easy as 1, 2, 3. So that's a very benign example, but it could be any instruction I would want to send to a system, and it's hiding almost in plain sight because, as we saw through the packet capture, the DNS records are plain text, but we have an encoded message. You can also encrypt that as well and have encrypted data going through there. I have an example of that. If you want to hit me up later on, I can show that. I'm running a little short on time here, so I'm going to skip that part for now. But let's go ahead and talk about exfiltration and see what that looks like. This is a packet capture of DNS exfiltration. And so sometimes exfiltration happens strictly through TXT format, but any DNS record type can be used for this. When I went through all the record types. So when you start seeing a lot of requests going to a lot of these gibberish subdomains, that's a good sign when you see repeated request after request after request. And in this case, we see the query down here, and it's actually going to a cisco-update.com host name. But we see tons and tons, and again, it's not human understandable, but when we see tons and tons of these kind of requests where it's these weird obfuscated subdomains to one parent domain, and we have a packet capture or DNS logs or proxy logs, and it's chock full and full and full of these, and it's not the same subdomain every time, that's a great example that you probably have DNS exfiltration happening where data is being converted to these strings and filtered out and reassembled on the back end, and it could potentially be a precursor to getting ransomware or something like that. So yeah, it can work well for command and control. It can work well for DNS exfiltration. There's some other DNS spoofing techniques. So ARP poisoning, again, if I specify the addresses network traffic's going to on the network, I can do the same thing for DNS resolvers. DNS server record changes. So if I compromise somebody's DNS hosting company and have access to their zone, I could change records, I could add my own subdomains in there, whatever I would want. Same thing with the domain registration itself. If somebody hacked the registrar where I have registered dfirmat.com, they could essentially change the authoritative name servers that the internet's using to their own malicious controlled ones and send traffic wherever they would want. So a number of ways to spoof DNS traffic. I'm going to talk real quick about amplification attacks. The idea is that you have a small request and the response that comes back is an overwhelming amount of data. And that is definitely a denial of service attack technique. Once upon a time, you could say type equals any when you made a DNS request, through anything, NS lookup, dig, whatever, programs, whatever it is, and it would return every record type for that particular host record. Threat actors abused it, and I remember the Open Resolver project reaching out when I worked at a hosting company saying, hey, you guys need to tighten up your DNS because you're allowing these huge requests to go back to a system and it's essentially flooding those other networks with traffic. And so amplification attacks, small amount of requests goes to a thing, large amount of data comes back. And if that happens a lot, you can absolutely kill a network. DNS reflection attacks, a little bit different technique. How this works is, let's say I am an adversary and I want to take somebody down. I want to knock them offline. I can essentially spoof the IP address of somebody's edge router, for example. So again, because UDP is a connectionless protocol, we don't have that three-way handshake, I can claim to be from any IP address on the internet I want to be, not necessarily where I'm actually at, and have the traffic go somewhere else. And if I do that across thousands, tens of thousands, hundreds of thousands of DNS resolvers, they're all going to send that information back to the spoofed IP address. So the people that are on our network are effectively down. They can't do anything because they've essentially been knocked offline. And looks like I did probably have time for that other demo. I'm going to pause here. Any questions so far? None? All right, maybe it's the sunglasses. I don't see any hands going up here. All right, let me see if I can get the other demo to work here. Usually I write it down because it's kind of ugly. So let me go ahead and come back here. And if I remember the address off the top of my head for... All right, so here is C2 for you and me demo.dfirmat.com. And again, I've got a long string, and it looks like that base 64 that I talked about earlier, right? So if that's true, then I should be able to effectively do the same thing and decode it, right? So I'm just going to replace the previous string with what looks an awful lot like what I just did. And I get an answer back, definitely an answer, but it's not human understandable still. So this isn't just simply, oh, I got a suspicious looking string, now I'm going to decode the string, and I get back the information I want. I get a result, but it's not maybe what I was hoping for to understand what's really happening. So this is a very simplistic example, but if I copy and paste the same string into CyberChef, and I throw some magic at it and see if it can interpret it, it doesn't really figure it out, but if I, oops, not that, but if I turn on intensive mode and let it crank a little harder, see if it actually figures something out here. So it's going to go ahead and bake that string and try to figure out what this human, not readable code is and what it actually does. And we get a whole bunch of different potential options. And so if I click on the first one here, because this is readable, the output is actually netsh firewall set op mode equals disable. What that's going to do on a Windows system is disable the Windows firewall across every profile, whether it's private network, work network, public network. And so that is a malicious command that would degrade the security on a particular host so that it's weakened, so I can attack it further, or I could have next stage malware doing something. And so what we see is that we have the base encoding like we guessed, but we also have it encrypted using XOR encryption. 2A in hex, well, that's actually 42 in decimal. So the key is 42 to do the XOR decryption rather. And so this is hidden much harder than the first example, which was only base encoded. This is actually using legit encryption. Now, in the real world, your malware sample is probably not going to be this easy to reverse, but that hopefully gives everybody an idea of just how well a lot of this stuff can be hidden. So I did have time to get the last demo. I'm grateful for that. We didn't have any questions last time. So with that, thank you, BSidesDayton!